Okay, so we are going to hear more about derivatives from Yongwei and their use in symbolic execution. Take it away, please.
Hi, everyone. I'm Yongwei Yuan from Purdue University. Today, I want to present derivative-guided symbolic execution. This is a joint work with my colleagues at Purdue, Zhou, Belyakova, and Suresh Jagannathan. Before we dive into derivative-guided symbolic execution, let's first look at a common mistake when we manipulate linked lists. When we try to remove all nodes of value x from a linked list, we might make a mistake and accidentally have one node to have two parent nodes. Well, how can that happen? Let's remove this element 1 from the linked list. To do that, we start from the beginning of the list, we iterate over the list, find the element 1, and then we remove element 1 by making its next node 2 the second node in the list. While this effectively removes node 1 from the list, it does not prevent this element 1 still actable elsewhere. So this is problematic. How can we catch this bug? Let's use symbolic execution. And before we dive into how this remove function is implemented in OCaml, let's talk about how we can represent it. First, we will use two key value stores. The first one is called n, which maps each node to its next node. The second key value store is called v. It maps each node to its value. And with this representation in mind, let's look at our function. The function has three main cases. First, if the list is empty, then we simply return the list unchanged. If not, we look at the value of the first node. If it's of value x, we simply return the tail of the list. Otherwise, we iterate over the rest of the list using a loop. And we remember our position using the previous node. At each iteration, we look at our current node. If we already reach the end of the list, we exit the loop and return the list. If not, we inspect if it is of value x, we remove the current node by skipping over it in the linked list using these put operations on key value store n. This put operation will create the invalid list structure we saw from the previous slide. We'll talk about it shortly. But whether the current node is of value x or not, we continue iterating through the rest of the list by return to the start of the loop. We will use this execution tree we just built to ground our discussion in the rest of the talk. And we will following the symbolic execution convention that we will use symbolic variables like n0 and 1 to represent the first node and the second node in the linked list as we traverse it. And we also need to finish the execution so that they terminate. And now we have two execution paths. The left one from the program point D, it involves the put operations on n, which, as we discussed before, it will create the invalid list structure. The right branch from the program point D, though reaching the same depth in this execution tree, it is safe because it merely traversed the linked list without modifying its structure. So really the question here is that which path should we take at program location D? At that point, we haven't explored the rest of the execution paths, but we want to have an idea of which branch do we take, which one is better. So let's talk about how can we guide the path exploration in a principled way. And our idea draws on the concept of derivatives from the formal language theory. And let's first define what are derivatives, and specifically, what are derivatives in our setting? Well, let's say we have a set of safe executions of the program. And the derivative of this set of safe executions over a program action is defined by the safe continuations following this program action. And using this derivative device, we're able to categorize the safe continuation at each program point as we traverse, as we explore the path in the program. And then, as an example, this is a execution we might observe as we execute the program. And this execution, it's merely traverse the linked list, right, using those get operations. So obviously, it's safe and included in the set of safe executions we saw on the last slides. And as the program inspects the first node in the linked list, this using a get operations on key value store v, we notice that this program action, it matches the first action in the safe execution. Therefore, the derivative will contains the postfix, the corresponding postfix. And as we continue exploring the path until we reach program D, we keep track of the derivatives and update it. And now we have two possibilities again. The left branch, again, it makes a put operations on key value store n, which does not match. Interestingly, it does not match the safe action in our execution. Therefore, the derivative becomes empty, indicating that no further actions are safe. And on the other hand, the second branch of D, it simply returns to the start of the loop, so the derivative remains unchanged. And when we look at those two derivatives, it becomes clear that we should take the left branch because it will definitely give us an unsafe execution down the road. With this intuition of derivative in mind, let's talk about how we can represent it. And we represent them using symbolic finite automaton. And let's start by constructing an automaton that recognizes the executions of the program. Let's say we start the program execution with two nodes A and B connected initially. What are the safe operations under this state? Well, it's obviously safe to reconnect A and B, or modify other parts of the linked list, or does not modify the structure of the linked list at all. It is also safe to first disconnect A and B using a put operation. And then, once we disconnect them, we're safe to perform whatever operation on those two nodes. On the other hand, there are also unsafe operations. If without disconnecting A and B first, if we assign B a new parent, then this will create the invalid list structure as we discussed before. And because we want to prohibit such invalid list structures throughout the program execution, we consider all future events to be unsafe. With this automaton structure in mind, it not only allows us to succinctly represent safe executions, it also allows us to represent their derivatives. As an example, initially, the initial state Q0 represents a derivative that contains a safe execution like this. It first disconnect A and B, and then assign a new parent to B. If the program indeed first disconnect A and B, then the derivative will update and suggest that, well, now it's safe for you to assign a new parent to B. On the other hand, if our program directly assign a new parent to B other than A, the derivative will correspondingly suggest no future actions are safe. Notice that automata here refers to those free variables like A and B, which is quite unusual for automata. Please see our paper for how we formulate this as a symbolic variant of derivatives. Now that we understand, well, safe executions and their derivatives can be represented using symbolic finite automata, let's return to our original path exploration problem and see how we can make the right choice. And we return to our same old execution tree here, and let's see how we can compute derivatives for various program points. As we enter the program, the derivative can be represented by Q0 from the automaton, because Q0, it represents all the safe executions the program is allowed to perform. As we follow the execution path to program point D, we iterating over the linked list and inspecting the elements in the list using those gets. And those get operations, it will match the self-loop transition in the automaton on Q0. Therefore, the derivative at program D is still Q0. The right branch of program point D, it simply returns to the starter loop. Therefore, the derivatives remain unchanged, and which is still Q0. On the other hand, the left branch, it will make the put operations on N, which attempt to remove the second node from the list, which is N1. And this put operation, while it will match both the left transition from Q0 and from Q0, we will prioritize taking the transition to the left, because that will give us more chance to find an unsafe execution. And the derivative at the left branch can be denoted by this best state Q2. We omit details on how we can generate constraints over A, B, N0, and N2, which are essentially path condition in symbolic execution. Please refer to our paper for details on how we generate those. But what really matters here is that with this derivative computed for both branches of program D, we're ready to make a decision. The left branch, the derivative suggests that, well, no future actions are safe. So we should definitely take the left branch, and indeed, we can find the unsafe execution towards left. By making this decision, we avoided wasted effort on exploring the rightmost execution path of the program, which essentially is iterating over the linked list without removing any nodes, so that it is not making any progress towards the violation of our unique parent property. So we avoid exploring that unproductive path completely. To evaluate our derivative-guided idea, we implemented in UCaml a symbolic execution engine that is called Hatch. We compare Hatch with two baselines. The first one is a naive symbolic execution engine implementation that does not leverage derivative. The second one is a recent work on whole automata type that is essentially a verification idea, but it's against a similar style of specification as we. We run all those tools on 10 abstract data type implementations that are implemented using various libraries, including key value store, list, set, tree, and graph. Among those abstract data types, we introduced 30 artificial bugs that will violate complex safety properties like the unique parent. And we observed that Hatch is able to find most bugs in 1 to 2 seconds. More importantly, Hatch is able to find those bugs faster. So the first two benchmarks are quite challenging, but still we are able to perform orders of magnitude faster than the two baselines. More importantly, there are more challenging benchmarks where both naive approach and the verifier either times out or runs out of memory, but Hatch is still able to find those bugs within seconds. To conclude, we we recognize that the safe executions of the program can be captured using symbolic finite automata. And the structure of the automaton allows us to compute the derivatives, which in turn categorize the safe continuations at different program points as we explore the path of the program. And those derivatives, in conclusion, provide principled guidance for path exploration in symbolic execution. And with that, I'm happy to take any questions.
Thank you. So I'll start with the question. So it seems like you use the automata to divide the state space, and in some cases, if you're fated to fail, like on the left side, then you want to go that way because whatever you do, you're going to be unsafe. And on the other side, well, you might stay in the safe space, but you still have the potential to fail. But what happens when, like, you have some red on both sides? Do you do some counting scheme, or do you like toss a coin? I mean, because you're not always fated to fail, I guess. You might have like more red states on one side, or
Yeah, that's a very good observation. And indeed, like you can even go back from a red state to a green state, right?
Oh, sure.
Yeah. So what we did in this work is we measure because each program point now have a corresponding to automata state, and we can measure the shortest distance to a bad state in the automaton. And we use that to prioritize, okay, which should we take?
Okay, so if going one way gives you a potential shorter path to a failure, you'll choose that. Okay, awesome. Okay, other questions? We have one in the back.
Thank you for the nice talk. So I'm going to ask a kind of provocative question. In the keynote this morning, Loris's keynote at the end, there was this idea about if an LLM is generating a program, it goes token by token, right? And it seemed like watching your talk, sort of from a high level, it seemed like you could apply these techniques in that context because you're receiving one token at a time, and you can sort of apply the symbolic execution on the fly with derivatives. Do you think that's an interesting idea, and is that something you have thought about?
Yeah, that's a very interesting observation because indeed, I think the idea of using derivative is not new at all. Like there are a lot of work on runtime verification, which essentially they have automaton which serves as a specification, and as our new events produced, you simply compute the derivatives of the specification. But I think it's certainly it will be if indeed if the specification can indeed be represented as an automata, and we can certainly use it as a guardrail to guide large language model. Yes.
Okay, good answer. Thank you.
Another question over here.
So thank you. My question is, what kind of semantics are you using for your language, and how do you have any correctness specification of this decision procedure? Well, not this algorithm.
Yeah, good question. So indeed, we are our setting is it's kind of specific, where those operations like put and get, their specifications are also defined by pairs of those automata. And so with that, I mentioned briefly to answer the second question, which is do we have any guarantee of this algorithm? I mentioned briefly in the evaluation that we have a naive implementation. So in the paper, we have two set of semantic rules. The first one is the naive one, which does not use derivative, and it's pretty straightforward. That operates over those automata. And then we have a second set of operational semantics rules that leverages derivatives, and we show that they are the derivative guided ones are sound complete with respect to the naive ones. Does that answer the question?
Okay, great. Thank you again.
Thanks for all the questions.